Welcome back to this video on Climate Mathematics, Theory and Applications. Today we'll be discussing the apply function and how it serves as an efficient alternative to for loops. In this section, we'll be calculating row means and also creating a function when you input a matrix of values that computes the sum of squared deviations, which is a statistical term that has huge importance in regression concepts, univariate concepts, and multivariate concepts. So let's begin. In this first section, we're going to compare the apply function to for loops, specifically calculating row and column means when you input a matrix of some dimensions. So in this first matrix, we're constructing a square matrix of 10 by 10 dimensions, and we're just filling it with numbers from 1 to 100, and we're entering it by row. So if you check out the previous video, which was important calculations using matrices, we discussed how to randomly generate numbers from particular distributions. And this doesn't come from a distribution, this is just straight generation of numbers that we expect. So here is matrix 2. As you can see, integers from 1 to 100, we entered it by row. Now let's use the apply function to calculate row arithmetic means of our matrix mat2. We'll store these row means in an object or a vector called row mean 1. Using the apply statement, we specify our input matrix, mat2, our margin, and since we're dealing with a matrix, which is a two-dimensional array, we only have two possible margins, 1 and 2. 1 stands for rows, 2 stands for columns. It's easy to remember because the dimensions of a matrix are always defined by rows, then columns. So 1 is for row, and here we see 2 is for columns. So since we want to find row arithmetic means, we specify our margin of 1, and for our function, because using the apply function we can specify a generic function like the mean, the standard deviation, the variance, or some other statistical or mathematical function. In this case, we want to find the mean, so we write that function, and calculating that, and printing it in our output, we see that for row mean 1, looking at the means of each row of mat2, so for the first row, our mean for that is 5.5. For the second row, counting up all these observations or summing them, then dividing by how many there are, the number of them, we see for the second row the arithmetic mean is 15.5. Nothing too special there, simple calculation, but let's do it using a for loop. So let's calculate the row arithmetic means of the matrix using a for loop. In this we'll initialize a vector, we'll call this row mean 2. It's always good to initialize vectors before entering a loop. It's just standard practice, good conventions, and it initializes something before you do an intensive process. In our for loop, we specify our iterating variable I, you can call this any variable, it's arbitrary, in 1 to the number of rows in mat2. Since we're calculating row arithmetic means, we use the nrow function, which automates the process, so we're not specifying the number of rows. And since we automate it, it doesn't matter the dimensions of mat2, however many rows we specify at the onset of mat2's creation. This automation process ensures those rows are going to be counted proportionate to what we entered when we created the matrix. So that's part of the automation process. So in this case, since we have 10 rows, we do from 1 to 10. So we increase from 1, 2, 3, all the way to 10, incrementing by 1 in our for loop. And we place our row means in that vector we created, initialized at the outset, row mean 2. In calculating our row means, we store each row mean in the vector, and since I represents 1 on our first run, we're going to store it in the first element position of the vector for our first row. And when I use the sum function, what this implies is I want the sum of the first row, the second row, the third row, iterating through the for loop all the way to 10, which is our last row. And I want the sum of this, so the sum of the first row, divided by the number of columns in mat2. Again, this is a way to automate the process, so I'm not specifying it every time I create the for loop. I just automate the process. I store the row means in the vector, and running this chunk of code, we see that using the apply function, we get the exact same values as if we were to use a for loop. So the for loop and the apply function yield equivalent results. Let's just check to see column arithmetic means. So if we didn't want to determine the means of a row, let's say that our samples were stored in the columns rather than the rows, we'd have to calculate column means. And we can do that using the apply statement, pretty much the same setup. Input matrix mat2. This time we specify our margin as 2. So 2 represents the column. We still want the mean. We're going to store that in the vector col mean1. And since we have 10 columns, we have 10 means. And looking back at this, the mean of the first column, which goes from 1 to 91, incrementing by 10, is 46. Mean of the second column, 47. Using the for loop approach, we initialize our vector col mean2, and in the for loop, we have our iterating variable I from 1 to 10 incrementing by 1. So in our first run of the for loop, we start in the first column of mat2, indicated by our indices here. We're going to sum up all elements within that column, and we're going to divide them by the total number of rows in matrix 2. We're going to store that value in the vector position 1, if we're on the first one. If we're on the second run of the for loop, the I becomes 2. We calculate the sum of elements in the second column, divide by the number of rows, and so on. And again, we see that our apply statement results are equivalent to our for loop results. So why would we want to use the apply statement when a for loop works best? The apply statement is defined in R, and when things are defined in R, it's a lot more efficient than defining a custom for loop. So that's why we can take advantage of the apply function, as it can perform redundant tasks better than a for loop, more efficiently than a for loop, and we can perform tasks of finding the mean, the standard deviation, and also more complex tasks, in which case we're going to define some custom functions. Let's say that we want to standardize all values in a matrix. How do we do that? Well, we subtract each value from the mean, and we'll just take the entire mean of the matrix, so we're not taking column means, we're not taking row means, we're taking the entire mean of the matrix, and we're going to divide it by the standard deviation of the entire matrix. An interesting thing when I wrote this apply statement is that it's still a matrix, it's still two-dimensional, but instead of going by rows or columns, I'm looking at each observation. And that's what the C statement does. When I say, alright, I want you to go by the first and the second margin by row and column, I'm looking at the element. So this is an element-wise operation using the apply statement. And that's how I specify something I want performed on the elements in a two-dimensional array. My function is custom defined, and if you go back to, I think, the first video on vectors, you can find more information on how to define functions, but we're going to call this a function of x being a matrix. We're going to subtract each value from the entire mean of matrix 2, and we're going to divide it by the standard deviation of matrix 2. Using this apply statement, here we see in our output, and remember we defined a 10 by 10 matrix, so the dimensions of it didn't change. This was an element-wise operation, and here we have standardized values that we obtained using the apply statement on each element of our input matrix. In preparation for calculating the sum of squared deviations from each row mean, I want to construct a function that calculates the mean vector and the mean matrix. So a mean vector, when we're talking about row means, is a vector, so it's going to be a column or row vector that contains each mean of the row of our input matrix. And the mean matrix is simply going to contain repeated values of the mean vector. So why do I want a mean matrix when I have the mean vector? Well, with the mean matrix, I can perform element-wise calculations that I couldn't do with the mean vector. And those element-wise calculations will come in handy when I calculate the sum of squared deviations, because I'm going to be subtracting my input matrix from my mean matrix. So let's do that. And take each step of the function creating process step by step. We will gradually build towards the ultimate function in calculating the sum of squared deviations. So I'm going to set my seed for replication. We're going to calculate pseudo-random variables from a uniform distribution, 100 of them, on the boundary 0 to 10. We're going to input them into matrix mat2 by row, and this is going to be a 10 by 10 matrix again. So if I take a look at mat2, these are the random numbers generated. We're going to call our custom defined function row mean function. It's going to be a function of a single variable, or in this case a single matrix, x. And we define our vector function containing our row means as mean vec. How do we calculate our row means? Oh, we can use the apply statement, input our matrix, right? Because that is our variable or our input. So I use the apply statement, input our matrix, calculate the rows, or go across the rows and calculate the means of each row. In the reps object, I'm using the rep function, and this is the repeat function. So in this repeat function, I'm going to repeat values of the mean vector n row times. And since I have 10 rows, I'm going to repeat each value 10 times. So what this means is I'm going to have a very long vector because the rep function stores these repeated values in a vector. But when I get those repeated values, I'm going to store them in a matrix. And when I store them in a matrix, I'm able to get the mean matrix, which is just a matrix of repeated values of our mean vector. So think of our mean vector as being columns, or one column, that's repeated in our mean matrix. And you'll get to see what I mean when we return this output. We're going to be returning a list. And a list is simply a vector containing different class types. So you have a vector which can only contain one class, but a list can contain different types of objects. So we'll call this list output. And in list output, we're going to output the vector of means and the matrix of means. So let's calculate the row means of matrix 2. So this entire function. Here is our mean vector. Here is our mean matrix. Now let's store this list in an object noted list1. So by storing the list, we'll be able to access metadata about what this list contains, whether it contains a vector, a matrix, a data frame. Keep in mind a list can contain different types of objects, different classes of objects. So by storing our vector and matrix in a list and calling that list list1, we can open that up, and here we see our mean vector and our matrix. I use this notation to access the mean vector and the mean matrix because look, the vector is stored as the first object, the matrix is stored as the second object in list 1. So when I print both of these out, here I see my mean matrix, here I see my mean vector. Take a look at our mean matrix too, by the way. What is our mean matrix? Well, if you go down, starting at the top, going to the bottom, and proceeding that way for each column, you see that our vector is repeated in the matrix 10 times. So our mean vector is simply repeated 10 times as a column vector in the matrix. And that's going to make element-wise operations possible. And we're now able to construct a function that shows the sum of squared deviations away from each row mean. So the sum of squared deviations is an important statistical concept. It's used in calculating the variance, the standard deviations, basically univariate descriptive statistics and multivariate descriptive statistics. So the sum of squared deviations is extremely important, and it also shows up as sum of squares calculations in regression concepts. So this is a good application to know, a good skill to know, and it's certainly important to see how these are calculated and a good application of using the apply statement. So we'll generate a new matrix. This time we're going to generate it from normal data, 153 observations, and normal data contains two parameters, a mean parameter and a variance parameter. In this case we just specify it as a standard deviation parameter. But we're going to generate 153 observations centered around a mean of 3 with a spread or standard deviation of 2 units. Here we have 51 rows, 3 columns, lines up perfectly with 153 observations. Let's create that. Generate those pseudo-random numbers, and so we can all see. Here is matrix 3. It contains normal data with a standard deviation of 2 and a mean of 3. Now let's calculate the row means. We're going to store those row means in a vector called meanVec. Our output. Now we're going to repeat those row mean values using the rep function into a vector of length 1 by 153. So remember, the repetition function or the rep function, it just repeats those values, and since we have 3 columns, it repeats the vector 3 times. So it doesn't generate new numbers, it just repeats the vector 3 times since we specified 3 columns. We just automated the process by calling in the ncol, or the number of columns function. We're going to store that in reps, and if you don't believe me about the dimensions or the length of the vector, let's type that out so you can see. And we have 153. So the mean vector was repeated 3 times. Let's enter our mean values by column, right? So recall that when we formed our mean matrix, we entered our mean vector as a column in the matrix, repeated for 3 times. Since we have 3 columns, that's why I said our mean vector is simply being repeated 3 times, and those vectors are being bound or binded together into a single matrix called the mean matrix. Our data is simply reps, specify our number of rows. It's going to contain the exact same dimensions as our input matrix, right, because we want to perform element-wise operations on it. So mean matrix, let's open that up, and here we have mean matrix. So as you can see, our means across the row are the same. Our column is just the mean vector repeated 3 times. So the important thing is our means across row are the exact same thing, and that enables us to perform those element-wise operations of calculating the sum of squared deviations for each row mean. Keep in mind it would change if you're calculating the column means. Now let's calculate the squared deviations and round that result to 2 decimal places. So squared deviations, how do we calculate it? Well, we use our original matrix, mat3, we subtract it from our mean matrix, and we square those values, all of which are element-wise operations. So it's not going to change the shape of our matrix, it's going to maintain those dimensions, but we're simply subtracting the original observation from the mean, that's called a deviation, and squaring that deviation. And all the round function does is it's going to round it to 2 decimal places. So let's store that in the matrix squared deviations. And here we can see. Mat 3, what was the first observation? 1.88 rounding to 2 decimal places. Mean matrix, 2.44 was the mean. 1.88 minus 2.44 squared, I should note that this is squared because we're dealing with squared deviations, is 0.32. So this matrix contains the exact same dimensions, rounded to 2 decimal places. And now we're simply going to sum these squared deviations across the rows, and we're going to store it in the object or the vector SSD, simply denoting sum of squared deviations. we'll use the apply statement. Since we want to sum this by row, our margin is 1, and our function is going to be the sum function. Store that there, and let's print these values out. Here we have our sum of squared deviations for each row. So that's pretty amazing. And using the apply function, it was efficient. We avoided for loops. We used the apply function. We were extremely efficient in the creation of these statistics for each row mean. Now we don't want all this code, we want to package it up into a nice function. We're going to call this function SSD, again denoting sum of squared deviations. It is a univariate function where you only have to input a matrix of x. Again, we specify our mean vector, initialize it, calculate our row mean vector using the apply statement, repeat that vector n column number of times, so however many columns we have, we're going to repeat the row vector by that, the mean vector by that. We're going to store those mean vectors into a matrix so that each column represents the mean vector for element-wise operations. Then we're going to perform the actual square deviation to obtain the squared deviation away from the mean. Here we have the sum of squared deviations, and since we're examining row means, we take the sum of the squared deviations across the row, and we're going to return that value, the sum of squared deviations. So let's take that and verify that what we put in our function is equivalent to what we got out in our code. And looking at our output, here we have what we had in our code, here we have what we have in our function. Our code and our function line up exactly, and that's what we want. As we move into chapter 3 of the book, these concepts are going to become very important as we measure various statistical properties. Again, congratulations. You just learned about the apply function, and I'll see you again in the next video. Thank you. I'm Ryan Lafler, and I'll see you soon.